Hello, welcome to the fourth video in the series going through the standard quiz model for AP Calculus AB from Term 1. In this video we're going to go through solving trig equations, a topic that's always been one of my favorites but typically isn't one that students feel as comfortable with. So I'm going to go through a couple different examples of different kinds of equations you might run into and some strategies for attacking them. Of particular importance I would say is probably C, just because that's something that comes up a lot. Possibly it's B, I'll have to look. I'll let you know. And then finally we'll do the plus question as well to get you prepared for the sort of challenges we might have in there as well. We're going to begin with question 4a, which asks us to solve the trigonometric equation over the interval from 0 to 2 pi. So we're focusing on the, one revolution or one cycle around the unit circle solution. And we're trying to solve the equation 9 tangent squared of x is equal to 3. So to begin with, a good strategy that I take in pretty much all equations is to try to isolate the main function or isolate the main type of operation. So in this case with tangent squared and stuff in there, I'm going to try to get tangent by itself. So I'm going to do a couple different things in here. First, I'm going to divide both sides by 9. So that's going to give me that tangent of x squared, or tangent squared of x, which is the same thing as tangent of x squared, is going to be equal to 1/3. And then I'm going to square root both sides. So now when I square root both sides, of course the tangent side itself takes care of things. But on the right side, we get the square root of something. We're basically plus or minusing both sides. We've got a positive and a negative possibility here, because both squared would give us the 1/3 we're looking at. So I'm going to write this as plus or minus square root of 1 over square root of 3. So you might write that as plus or minus root 3 over 3. I'm going to leave it as it is. So we're looking for all the angles, positive or negative, or all the angles from 0 to 2 pi that give us a tangent of either positive or negative 1 over root 3. So to start this off, I'm going to draw in my little coordinate plane, kind of my unit circle. I'm going to draw in the triangles we're going to be looking at here. And I'm going to need 4 of them because each possibility, plus or minus, is going to give us 2 possible quadrants or 2 possible angles. So in looking here, if we take any one of these triangles, we can figure out what the reference angle is going to be by using that ratio. Tangent, as we've said many times before, is going to be opposite over adjacent. So that means our opposite will be 1 and our adjacent will be root 3. And looking at this, the angle we'd be looking at, the reference angle itself, or the angle in quadrant 1, is going to be whatever's opposite the 1, which is going to be a 30-degree reference angle, also known as pi over 6. So basically this is going to give us the 4 pi over 6 reference angles, or angles that have that reference angle of pi over 6. So basically, without having to do a whole lot more work, I'm going to get 1 pi over 6 for each quadrant. It's going to give me pi over 6, 5 pi over 6, which is also known as 2 pi minus pi over 6, 7 pi over 6, otherwise known as pi plus pi over 6, and finally the last one down there, which is going to be 11 pi over 6. So these are the 4 angles that we'll get that are solutions to this equation. So pretty straightforward. It was all about isolating that trig ratio, or the trig function itself, which in this case was tangent, and not forgetting the plus or minus and the possibilities that are created there. So there is 3a. For 3b has a little bit more going on here. This one's got 2 cosine squared plus 5 cosine minus 3 equal to 0. So we have almost a polynomial kind of structure. And in fact, that's where I'm going to begin. Even before I do anything fancy here, I want to try to think about this as a sort of polynomial. So I'm going to kind of imagine it for a second as something like 2t squared plus 5t minus 3 equals 0. My thought process being it's just a little bit cleaner to factor when I do it that way. So in here, if you're a diamond person or not, basically we're looking for 2 numbers that multiply to negative 6 and add up to 5. So multiply to negative 6, add up to 5. That's going to give me, let's see here, we're splitting the middle term, we're going to get plus 6 and then minus 1. So there would be our t version that we're looking at. In fact, I'm going to get rid of the 0 here. But basically there is our broken up middle piece. Let's see if that actually works. We got 2, 2, 2. Yes, it does. It's a good sign. So now I'm going to convert it back to cosines. So we'll have 2 cosine of x squared, or 2 cosine squared of x, plus 6 cosine, minus cosine, minus 3. And of course we want to factor this so that when we set it equal to 0, it's easy to use the zero products property to get our way through. So in here, looking at GCFs and what this would factor to, lots of different ways to get there. Do it as quickly as possible. We're going to get 2 cosine of x minus 1 for one factor, and we're going to get cosine of x plus 3 for the other factor. So there are 2 factors that we're going to have to figure our way through. So in looking at each of these two possibilities equal to 0, the one on the left is going to ask us to solve the equation and determine when cosine of x is equal to 1/2, at least for x between 0 and 2 pi. The other one, though, is going to be when cosine of x is equal to -3. Now, on this right side, cosine of x equals -3 is actually an equation with no solution. The reason is, the cosine function, because it's the ratio of an adjacent side and hypotenuse the hypotenuse has to always be longest, the cosine's value or magnitude has to always be less than or equal to 1. So therefore, that's actually going to give us no solution. So there's nothing here for us to actually solve. So we're going to have to focus instead on the cosine of x equals 1/2. So doing a quick little analysis here. Again, this is usually what I do. I actually look at it this way. So if cosine is positive, since 1/2 is a positive ratio, that's going to give us, of course, one angle, x, in quadrant 1. But then cosine is also positive in quadrant 4. So we're going to have two different angles, one in quadrant 1, one in quadrant 4. As far as our angle pieces, cosine is 1. That makes the hypotenuse 2. That means this is root 3. So in this case, we're opposite the root 3, which means that our reference angles are going to be the pi/3 reference angles. As far as our values, the first one's in quadrant 1, so that will be literally pi/3. The second one will be down in quadrant 4, which is going to be 5 pi/3. So we have only two solutions as it turns out. The two 60-degree reference angles, pi/3 and 5 pi/3. So that hits part B. Now part C. Part C feature is one of my favorite types of problems. Unfortunately, it's not one that people do well. So I'm going to make sure to talk about the theory behind it as well as we go through this. So it asks us to solve the trigonometric equation 8 sine of 2x plus 4 equals 0. And now I'm going to ask you to first just kind of bear with me. If we subtract 4 and divide by 8 on both sides, we'll get the equation sine of 2x equals -1/2. So I'm hoping you can get to that point. Now this is an important place to be. If this just said the sine of theta equals -1/2, this would be a traditional problem where we just kind of slap on the stuff, we go, well, it's negative, so it's down here and here, and we just finish out the problem really quickly. In this case, though, because of that 2 in there, that 2 actually changes an important part of this graph in this function's behavior. In fact, it changes the period. In other words, this thing repeats its behavior, its entire shape, its perfect pattern, it repeats on a much shorter interval. And to find that period, we take the number 2 pi and we divide it by that internal coefficient in the argument, which in our case is 2. So our period in this case is going to be just plain old pi, which means on the interval from 0 to 2 pi, whatever the shape is, we're going to have one set of repetitions followed by another set of repetitions before we run out of space. So we are going to have to take this into account as we work our way through. So keep that in mind as we go. Next, though, if sine of 2x is equal to -1/2, then that means 2x is going to be equal to whatever the angles would be that gave us that sine of -1/2. So again, following that same kind of pattern we have before, sine is negative in quadrants 3 and 4, just like the y values are. Looking down here, if sine is 1/2, that's opposite over hypotenuse. So we are opposite the 1, which means that we've got 60-degree reference angles. And doing some simple work, you could very quickly figure out that one such angle would be 7 pi/6, and one such angle would be the one in quadrant 4, 11 pi/6. In fact, we saw these in part A of this particular question. So at this point, we have 2x equals those two angles. We're supposed to expect more, but for the moment, we'll just play along. And what I'm going to do is I'm going to multiply both sides by 1/2. That way we can at least get a couple solutions here and get ourselves started. In particular, we'll get that x is equal to 7 pi/12 and 11 pi/12. So those two angles are our first two solutions. The problem is, as we said, because that period has changed, there's a shift in the period and it's gotten smaller. That means that the graph repeats itself multiple times on the interval from 0 to 2 pi. In fact, it's going to repeat itself twice. So we have those two solutions, and they're very important solutions. We can't get the other two without taking into account the period. So basically, for the moment, we're stuck with 7 pi/12 and 11 pi/12. But remember, trig functions repeat themselves every period. So it's going along whatever the value is here. One period later, it's going to have the exact same function value, or y value. So in this case, if we want to find the other two solutions, we need to take those two solutions, and we need to add the period to them. So in particular, we're going to add pi to each of those solutions, and that will give us our 4 solutions. But of course, we don't want to just settle for 7 pi over 12 plus pi. That just looks kind of ugly. It's not like it's wrong. It's just not what I'm settling for. So instead, what I'm going to do is I'm going to think of that period as a common denominator. We're just going to add two fractions together. Pi over 1 is the same thing as 12 pi over 12. And the same thing here. Pi is just 12 pi over 12. And that means that we can get our four solutions. Of course, our first two that we were able to solve for very quickly, 7 pi over 12, 11 pi over 12. And then our other two, which are going to be 7 plus 12, which is 19 pi over 12. And then 11 pi over 12 plus 12 pi over 12, which is 23 pi over 12. And there are our four solutions. So we have our four solutions to this particular equation. So and again, the important thing here, the new piece that we have to take into account is that period. So as soon as you see some coefficient that isn't 1 inside that argument, and specifically coefficient, by the way, just that scalar, that tells you that you're going to actually have to do some sort of adjustment like this and take the period into account. So in order for us to get all four solutions to this equation. Typically, by the way, in the standard quiz, I will tell you there are four solutions just to kind of remind you and kind of jog your memory, but you might not have to, might not. Okay, so that brings us to the plus question. So this one asks us to find the minimum positive solution to a very funky looking equation. Let's just call it what it is. So with these equations, you can sometimes be intimidated before you even start and think that this is much harder than it is. In truth, this is just the same kind of equation. We've just got extra algebra to do. That's all the plus question typically involves here is extra algebra. So to start with, I want to solve this equation and make it as clean as possible when I first begin. To start with, I'm going to ask you to realize that we could subtract pi from both sides. Like a bakery that's selling well, we could subtract pi. And then we could divide both sides by that negative pi over 2, pi root 2. So by doing this, again, I'm kind of speeding through some of the more tedious parts of this calculation. We could end up with the cosine of stuff is equal to negative pi over negative pi root 2. And of course, that will simplify to 1 over root 2. So 1 over root 2, which you may know as root 2 over 2, is the pi over 4 reference angles ratio for cosine as well as sine, as it turns out. So basically, right at this moment, we're trying to figure out the cosine of some angle is equal to 1 over root 2. If we want the minimum positive solution, that means we want to have smaller angles. So where I'm going to start here is I'm going to point out that if the cosine of something equals 1 over root 2, then that inside argument has to be equal to that minimum angle. So in other words, it's got to be equal to straight up pi over 2, or pi over 4, excuse me. From here, we want to solve this equation as best we can. And again, you can see this isn't going to be the prettiest equation in the history of the world, but that's okay. We can make it work. Still a functional equation. I'm going to multiply both sides by 13. That'll give us x squared plus 5 is equal to 13 pi over 4. Now I want to subtract 5 because I'm trying to get x alone. I'm trying to find the smallest angle there. So I'm going to subtract 5. When I do, I get that x squared equals 13 pi over 4 minus 5. There's other ways you could write that. We'll deal with them in just a second. And then finally, we want the minimum positive solution. So when I go to solve for x, I'm going to square root both sides. I only need to consider the positive because we're talking about positive solutions. And we'll get that x is equal to the square root of 13 pi over 4 minus 5. Now, if you are a common denominator kind of person, that's fine. You be you. We could get a common denominator of 4 in this case, and we could get 13 pi minus 20 all over 4. Or if you wanted to go even further than that, since we have that square root of 4 is 2, you could even write this as the square root of 13 pi minus 20, all divided by 2. So lots of correct answers, but of course we're looking for correctness above anything else. So if you chose not to simplify, that would be okay. And with that said, that covers the fourth question on the standard quiz model, which is talking about solving trig equations with a couple different little tricks and twists that might actually pop up.